understand both the physical oceanography and the biological oceanography of the ocean interior. For the most part, I've steered clear of the boundaries, the seafloor, the sea surface, but not exclusively. All right, so I would say that my main interests right now are sort of at the intersection of where physical oceanography at a variety of different scales, mostly sort of sub-mesoscale and smaller, how those scales impact ecosystems and the inhabitants of those ecosystems. So we're now in an era of new mobile and autonomous platforms. So if you look up here in the top right-hand corner, I have a little bullet that says mobile acoustics. And, you know, these include AUVs, gliders, wave gliders. There are ocean observatories, drifters. And what I'm really interested in is taking all these techniques that we've been developing, these acoustic scattering techniques, and really sort of transitioning them into a variety of different platforms. Okay, so most of my research has been right here in what I call my backyard. So everything from the Northeast US coastal regions, I've worked in really shallow regions like the Connecticut River, all the way out across the shelf to the shelf break and the canyons. And this is sort of what I consider to be my backyard. I'm really interested in developing new platforms that will enable us to further understand these regions. So this is a region which has undergone significant warming over the last decade. The Gulf of Maine has warmed more in the last decade than 99% of the global oceans. There have been, so it's believed that part of this is due to the northward shift of the Gulf Stream, at least in part. And what's really uncertain is, as a result of this warming and variability in the physical oceanography, how are ecosystems going to respond? And how are we going to assess that response? And so there are going to be, a lot of organisms are going to behave differently. They're going to shift their cycles. And, developing sensors that allow us to get at these is going to be important. My sense is that we're also at a time when some of these processes that are impacting the ecosystems that we're interested in occur on relatively short timescales. For example, you might have a warm core ring which interacts with the continental shelf. And if you want to know what the impact, say, of that warm core ring is on the migration of squid, you're going to have to be able to get out there on a relatively short timescale. You're not going to have the luxury of scheduling ship time on the Neil Armstrong a year ahead of time in order to sample that particular event. So my hope is that we're going to get to a point where we can use acoustics, which, by the way, I think is, in my opinion, a pretty good tool for getting at a really integrated view of ecosystems, mostly because there are a number, you can put temperature, salinity, fluorometer, you can put a dissolved oxygen sensor onto a vehicle, but it's very hard to assess zooplankton and fish at the same time. And acoustics is one of those remote sensing tools that allows you to integrate all of that information together. So the point of my talk is basically going to be, how do I take, or how do we take as a community, everything that we've learned about acoustic scattering and applying acoustic scattering techniques and putting them onto these new platforms that are becoming available to us. And so what I'm going to do is I'm going to pick a few examples of research that I've done which illustrate some of the different platforms that you can use. However, the one last thing I want to mention is something that I've been very involved in over the last year or year and a half or so, is what happens when you get to the edge of the shelf and you go over the shelf break and into the deep water. And so one of the regions that I've been spending a lot of time working in is, or working towards, is the twilight zone, the mesopelagic zone. And so there was a really interesting paper published in 2012 by Cardvert, and that was in MEPS. And he showed that the biomass of mesopelagic fishes is likely to be underestimated by at least an order of magnitude due to avoidance. And then in 2014, a paper by Irigoyen came out that showed that there was a very tight correlation between biomass of mesopelagic fishes and primary production, suggesting that the role of these organisms in biogeochemical cycles has probably not been fully understood. And so it really got me thinking that there's really a technological void right now for really understanding the mesopelagic zone, which is probably somewhere between 200 meters and 1,000 or 1,500 meters. And so you can't really just use shipboard acoustics because sound is attenuated sufficiently that you're really selectively seeing the behavior of certain organisms. You can't just use trolling because you have avoidance, and you're not going to sample sort of fragile organisms, the jellies, the ctenophores, siphonophores, those aren't going to be well sampled. And so developing tools that will allow us to get into this habitat and really understand the biodiversity, the abundance, the behavior is something that I've been working on, and I will show you, even though I don't have data there yet, we are developing an instrument, and it's pretty much, it's close to being completed, and I will show you our progress on that. However, I need to go back to my base. I'm not a biologist, and I'm not an oceanographer. I'm a physicist by training, and my expertise is really in the scattering physics and in developing tools that allow us to use this acoustic scattering to look at the ocean interior. So what you see here is target strength as a function of frequency. This figure is by no means comprehensive, and I am certainly not the only person who has contributed to the models in here. And what you basically see is that there's great complexity and diversity in what the scattering from different organisms look like. And the good thing about that is that it gives us hope that we can use these spectra, if we can measure them, to distinguish and characterize organisms and physical processes. So some of the things that are worth remembering for this talk, because they'll come up again, is that there are different regimes. So for example, if you look at bubbles, or if you think of a fish with a swim bladder as a big bubble, you'll see that there's a scattering. Let me see if I can find my mouse again. You see that there's a lower frequency resonance frequency, and that above that frequency you have a generally decreasing scattering spectrum. Most of the biomass in the ocean is weak scattering organisms such as krill and copepods, and you'll see that they have sort of frequency to the fourth power response in the scattering, and we call this the Rayleigh scattering regime. And then you can see that as you go higher in frequency, the scattering becomes more complex. You really are dependent on not just the material properties, but the details of the size and the shape and the distribution and the orientation, and these things become important in predicting the scattering. And so what I'm really interested in is taking techniques that allow you to measure these spectra and putting them on different platforms that allow you to address different relevant questions. Okay, so a little bit about broadband signal processing, just because we're going to need this to understand the data that I show. So the idea with a broadband signal is that you transmit a signal that has frequency content across a range of frequencies. Here, for example, you see a signal which starts at low frequency and goes up to higher frequency in a linear fashion, and we call this a chirp. You can see this frequency response of this chirp, and the frequency content of this particular signal is approximately 40 to 100 kilohertz. In fact, the frequency response of a system is not dictated by the signal that you use, but by the hardware. It's determined by the transducer, the filters, the digitization. All of these things together determine what the bandwidth of your system is, in addition to the signal. Now, the nice thing about broadband processing is that not just can you get the spectrum, so you can get the scattering across a range of frequencies, but if you do match filter processing, you can actually increase the range resolution of your data. So, and match filter processing basically just means correlating the received signal with a replica signal. And it both increases your signal to noise gain, which is great, but it also increases the range resolution of the measurements that you have. So for example, if you look at this signal all the way on the left, figure A, this is about a 2 millisecond long signal. So if you were just using a narrowband signal, the range resolution of that would be about 1.5 meters. Whereas after match filter processing, and you can see this is the result of the match filter, your effective time resolution is much smaller, and so your spatial resolution is smaller too, which is great. So it means that you can see, you can resolve smaller scatterers. So how did that look? This is an echogram. This is actually data from the Neil Armstrong. This is the EK80 broadband system on the Neil Armstrong. You have depth on the left and time along the bottom, or ping number. And what you see is the Armstrong was steaming at about 6 knots, and this is what you see at this on the left-hand side of this echogram. And then you see that we transition, we arrive on station, we slow down, and we switch from broadband to narrowband mode. And we actually did that to deconflict with a broadband ADCP that was on our CTD cage. So what we were really interested in was these scattering layers that you see, and we were interested in how those scattering layers correlated with the steps in the temperature and the salinity that we saw in the CTD profiles. But what I really want to focus on is you zoom in on this section. This is a zoom in right here, and you can see that the resolution of the signal decreases when you go from broadband to narrowband, and furthermore, some of these layers disappear below our noise threshold. So, this is just one illustration of why broadband acoustics are beneficial in terms of the range resolution. And you might ask, well, so who cares? They're pretty narrow layers either way. But if you have say a 2-degree temperature drop across 1.5 meters versus a 2-degree temperature drop across 10 centimeters, that's a very big difference from a physical oceanographic perspective. Okay, so what I want to do is I just want to describe some of the platforms that I've been using to do my research. So when I started doing this work in broadband acoustics over 10 years ago now, so I had this system in 2005, I think is when I purchased it. The first experiment was in 2006. And this was a broadband system, which is basically a heavily modified off-the-shelf system from EdgeTech. So the system electronics, I didn't really change enormously. I added transducers, but the basic hardware didn't change over the decade that I used this system. However, the platforms that I put it on changed significantly. The very first deployment over here, for example, was I deployed the EdgeTech system with the transducers downward looking, and this was a profiled system. Later, I bottom mounted it and just put it out at an observatory, bottom mounted for a month, collecting data. I've pole mounted it. I've put it into a towed platform. I've put it onto an ROV, and my postdoc, Chris Bassett, actually put it into an under ice experiment for a couple of months, and it collected data of oil under ice. So this system, the system, like I said, didn't change very much, but the platform changed enormously, and as a result, the science questions that we could address also changed. So another thing that I'm going to be talking about is where the field is going in terms of adopting these broadband techniques. I was delighted when Kongsberg Simrad came out with their broadband system, and that was in June 2015. And there's a very fancy broadband system on the Neil Armstrong. In fact, if you go into the Neil Armstrong, it's a bit like a walking advertisement or floating advertisement for Kongsberg. But I've been doing these broadband measurements for 10 years. So though it's great that they have these ship-mounted systems, the thing that I'm really excited about is actually these 2 systems which are on the bottom right-hand corner. These are also Simrad systems, but they're much more versatile. They've put the electronics into this system that they're calling the WBT2, which is the wideband transceiver in a tube, I guess. This is an 8-channel system, but this is something that you can really begin to move around in the same way that I move my EdgeTech system around, and you can begin to put onto different platforms. Even better, they've come out, I think this is a fairly recent development, I think I only saw this in the last few months, with the WBT Mini, which is a 10-centimeter box with 4 cards, 4 broadband transceiver cards, which you can pretty much do whatever you have the imagination to use them for. Okay, so what I'm going to do now is I'm going to pick a few experiments that I've done over the years, moving from these first initial sort of profile deployments all the way through to some experiments that I've done with these new SIMRAD wideband transceivers, and the different platforms that I've used and the different science questions that we addressed. So the very first experiment that I did was the Shallow Water 06 ONR funded experiment. This was a gigantic experiment. It was one of the lead PIs was Jim Lynch, and he claimed that there was a seawater level rise as a result of all the instruments that went into the water. Not sure if that's true or not, but my own component of that was to participate with a physical oceanographer on the Jim Moom on the RV Oceanus. And the idea here was we were interested in the generation, propagation, and dissipation of internal waves as they propagated over the New Jersey continental shelf. And in the bigger picture of the acoustics experiment, the idea was what was the impact of these nonlinear internal waves on acoustics, different aspects of acoustics. So I put my profiling system in, and we would sample the internal waves. And then as the internal waves passed us, we would pull up all the instruments, and then we would get ahead of the internal wave. And so every internal wave train was sampled multiple times as it traversed across the continental shelf. Jim Moom had an impressive suite of microstructure profilers to have direct measurements of the microstructure. And I had a team of people who did the zooplankton sampling so that we could assess what the contribution to scattering from zooplankton was. I'm going to pick one example of the many that 27 internal wave trains were chased, and they were each sampled multiple times. So this is just one example. On the left, you see 4 echograms. This is basically the output of the match filter as a function of depth and time. This is on August 14th, 2006. Jim Moom named all his internal waves. This is Mica 1. And you see 2 little boxes. I've indicated them as box 1 and box 2. And what I was interested in was, can we characterize can we identify and characterize the scattering mechanisms? And so what we found was that the trailing edge of many of these internal waves had very strong scattering, and the scattering spectrum, which is what you see here on the right, which is volume scattering strength as a function of frequency, and you can see that that is consistent with a scattering model for temperature microstructure. Whereas underlying, so these internal waves are traveling basically at the thermocline, and below the thermocline there was a strong scattering layer which was generally increasing with increasing frequency and was consistent with scattering from zooplankton from the net toes. And so we were able to show that you could actually invert at high resolution these scattering measurements to obtain dissipation rates, which were consistent with the dissipation rates that were measured with the direct microstructure profilers. So this was great, and this was the first example that I knew of using high-frequency broadband acoustics to look at microstructure and distinguish it from zooplankton. And so that resulted in a couple of papers, but it really got me thinking about a couple of things. And the first thing that I was thinking about was I had been developing scattering models for microstructure that included both temperature and salinity, and the results of that model suggested that at high frequencies, salinity microstructure would have a very large impact on scattering. And so I wanted to go to an environment that was not so thermally stratified, but had more of a salinity stratification. And the other thing that I was interested in was in capitalizing on that very high range resolution that we could get with the broadband acoustics. So I worked with my colleague Rocky Geyer, who's an estuarine oceanographer, and we went out to the Connecticut River, and the Connecticut River is a salt wedge type estuary, so it's very highly stratified. And I basically took this, this scattering system and I pole mounted it. I'm not sure if a pole mount is a platform, but for the purposes of this talk, pole mounting is a platform. And so I pole mounted my, my broadband system on the RV Tioga. And Rocky Geyer has this monstrous mast. It's a 10-meter long mast with 8 sensor brackets and microstructure sensors, so that he could characterize microstructure in the water, and I could characterizing it using acoustics. The water depth is on the average about 5 meters, can be as shallow as 2 or 3. It can get up to about 10 meters outside of the mouth, but for the most part, it's pretty shallow. We did have a microstructure profiler with us. Unfortunately, you can't really stabilize the microstructure profiler before it hits the bottom. So we didn't really collect good measurements with the profiler. So even though these are highly accessible environments, they're actually challenging to work in. And so we went back to the Connecticut River. I went back to the Connecticut River this year. I've been working in the Connecticut River since about 2008. And it's a backyard experiment. It's a fantastic place to work. And so one of the first things that we saw were very spectacular high Reynolds number shear instabilities. And part of the advantages of using broadband acoustics is that very high spatial resolution, which allowed us to get measurements which allowed us to begin to understand the dynamics of these instabilities from a purely imaging perspective, not even getting into the details of the scattering. And so Rocky published a paper on that. And my own interests were more on the scattering physics side of things and how do we characterize the microstructure that we were seeing, and was it consistent with my scattering model, which included salinity microstructure. And so here what you see on the left, you see 2 echograms. This is depth and a function of time. This is on the 17th of November in 2009. And on the right, you just see a similar location just a day later. And what we found was that the scattering was divided basically into 3 groups. We had basically scattering that was consistent with salinity microstructure. We had a pretty strong signal from suspended sediment, which was increasing as a frequency to the 4th power. And then we had fish. We had schools of fish with a generally decreasing scattering spectrum. And we were able to invert those microstructure measurements with no free parameters because we had measured the temperature and salinity profiles and pretty accurately reproduced the salinity dissipation rates that we were seeing, salinity variance that we were seeing with the microstructure profiler. So this was great, but like I said, it's not really a platform. And so I've chosen this example as putting my EdgeTech broadband system onto a towed system. So in the bottom left-hand corner, you can see this towed body. It's really rather ugly. We called it the hammerhead. And it was a towed system. This had a coax cable, and it was depth rated to 500 meters. And we deployed it on 2 enormous ocean acidification and pteropods studies. So the idea was that we were interested in shell-forming planktonic organisms, sea butterflies. These have elastic shells, and so in proportion to their size, they scatter sound very effectively, but they're also impacted by ocean acidification. And so this study was basically setting a baseline for their distributions and abundance in relation to the ocean acidification that we were measuring. So we had a team of chemists in addition to acousticians and biologists on these cruises. And again, I'm just going to pick of those 2-month-long data sets, I'm going to pick one 5-minute period to show you data from. On the left, you see this is range from the hammerhead, year, day, or time across the bottom. You see 2 echograms. One is the 80 to 120 kilohertz, and the other is the 220 to 300 kilohertz subsystems. And you can see that there's that the scattering looks very different in these 2 different frequencies. And so we picked different regions. We did net tows, and on the right you see broadband spectra for these different regions. So that's volume backscattering is on the left. You can see that this is about a 60 dB range, and the frequency is on the right. And we had frequencies in this cruise. We had increased the frequency range to span about 50 to 600 kilohertz. And what you see is that there were very distinct scattering spectra. These frequencies are perfectly matched for krill. That's the gray data with the green line. The green line is the inversion using a scattering model of those data using, this is a fluid-like scatterer. And using that model, we were able to invert not just for the size of the krill, but also for the number of organisms. And we found that it agreed very well with our net till measurements. It turns out that for the pteropods, this is actually a forward calculation. The red line, so you see the data are in blue, and the red curve is actually a forward calculation based on the size of the organisms that we saw in the net. So it looks reasonable, but we were not really comfortable doing an inversion because we're basically entirely in the geometric scattering regime. And so we couldn't really, or almost entirely in the geometric scattering regime. And so we couldn't really get at the size of the pteropods. And so, we didn't feel like we did a good job sizing the organisms. It would have been nice if our system had gone up to maybe a megahertz. Another thing we saw, which comes back to these mesopelagic organisms, we saw these spectra, which is in the magenta curve, which we think are mesopelagic fish. We only had zooplankton nets, so we didn't catch any mesopelagic fishes, likely because they avoided the nets. They're very strongly frequency dependent. You can see that the spectra decrease almost 15 to 20 dB over this frequency range. So we think that that's likely swim-bladed organisms, and in addition to beam pattern effects. But because we don't have scattering models for many mesopelagic fishes, and we didn't catch any with which to do any kind of sort of informed modeling, we sort of left it as we don't really know. All right, so I now want to talk a little bit about transitioning from my own broadband system, which was this sort of modified off-the-shelf system developed by EdgeTech, which, though very useful, hasn't really taken off in the community. And so when Simrad started working towards their broadband system, we worked with them to sort of beta test their WBTs before they came out in June 2015. So I'm going to talk a little bit about this experiment, which we did using the Simrad WBTs. The idea was at the time to look at distinguishing squid from butterfish and characterizing the abundance of butterfish. Part of the reason was that when we wrote the proposal in 2013, butterfish, the butterfish fisheries had been shut down because of low abundances of butterfish. In fact, they've come back since then, and there's now a pretty active butterfish fisheries. But in any case, they were often caught as bycatch for in squid catches. And but it turns out that when we went out, we never saw squid either in the trolls or in the acoustics. What we did see were dogfish and krill. So this is not a squid butterfish project. This is a krill butterfish project. We actually did this with all of these Simrad transducers, which you see over here on the right. We literally put them onto a sled and towed the sled with cables coming up onto the vessel and the WBTs on the deck. We went out on the FV Karen Elizabeth, which is a fishing vessel. This Chris Roebuck, who's the captain, is actually a butterfish and squid fisherman. And so we went out to these different canyons, and we did some trolling so that we could ground truth the acoustics. And this is Atlantis Canyon. We saw a lot of krill in Atlantis Canyon. This is a patch of krill. You can see these very high volume scattering strengths, minus 50 dB. And so clear signal. The question was, what about butterfish? Well, so the butterfish that we found were in Alvin Canyon, and they were down fairly deep, and they were hard to see at the very highest frequencies that we had. And what we measured was this rather strange spectrum, which I have to admit I didn't believe when I first saw it. I thought there must be something wrong, either with our calibration or our data. But that was what we measured. And we also saw this layer, it was fairly pervasive, which very low scattering levels. It was about a minus 50, it was, minus 80 dB, slightly decreasing with frequency. And, you know, my response to that is it's probably gas bearing, but I don't really know. But going back to the butterfish, we dug around in the literature a little bit. And so what I've drawn here is a chi by eye curve. There's no scattering model. All I have done is sort of done a best guess fit. However, if you dig around in the literature, Corneliusson published a macro model. Mackerel is also swim bladder-less fish. And the scattering model you see in the blue curve on the bottom right-hand corner, and it has that same slightly odd pattern. And the suggestion here was that this lower frequency component is basically the flesh, and then as you go up to higher frequencies, you get a contribution from the bone structure. In order to make this work, you have to incoherently add those two contributions. And so I think the take-home message from this is that there's lots of work to be done with developing scattering models for mesopelagic fishes and butterfish and so on in order to correctly interpret the acoustic scattering measurements. So now I want to talk about a different set of platforms. So we use the WBT transceivers, which are the shipboard transceivers. But like I said, Simrad put out what I think are really this rather nice system, the WBT Mini. The cards are quite compact, and they're a good size for putting onto a Remus. And so the idea for this is that we have a project funded in the Connecticut River to look at the dynamics of fronts. And these fronts are surface associated. And so we wanted to get an instrument under the fronts so that we could sample from beneath the fronts. So this system, so we put the WBT Mini into a Remus 100 housing. We had two transducers. These are the new Simrad transducers, the mini transducers, the 200 kilohertz and the 333 compact 7-degree beam width transducers. The nice thing is they're substantially smaller than the ones that they've been using to date. And we put, so if you look at the front end of the Remus, that's got the transducers on it, and we could actually rotate that section so that we could point the transducers in whatever direction we wanted. In this case, they're pointed down, but we could also rotate it and have them point up. There was some communication between the computer in the acoustic section and the actual Remus. So the Remus turned the system on and off when it got to a certain depth. It provided us with a GPS timing signal so that we could synchronize the data from the Remus and the acoustic data. And it also provided us with power. So this is the Connecticut River. This is the mouth of the river. We actually used the Neil Armstrong. We used it as a big hotel. It basically parked out in Long Island Sound. And we had a flotilla of small vessels. So my own Remus was just one of 6 Remus vehicles out there. We also had a colleague, David Honegger from OSU, who had an X-band radar. And so you could see this front, which develops. So during the ebb tide, fresh water is coming out of the Connecticut River. And as the tide in Long Island Sound begins to ebb, you can see that you get this front forms. So there were 2 vessels that we had, the R&R, which had my Remus 100 on it with the broadband acoustics, and the Dawn Treader, which had environmental in situ sensing. And you can see this front, and the idea is the questions we wanted to address are, what are the dynamics of the front? How fast is the front propagating? What does the front look like in 3 dimensions, in the vertical and in the lateral? And how much mixing is occurring at the front of this plume, of this freshwater plume. This is just a picture of what a photograph of what that front looks like when you're down on a vessel. This is the Dawn Treader. The Dawn Treader had a CTD chain, a 1.2 megahertz ADCP. Then we had this multi-beam, this 500 kilohertz Simrad multi-beam, which we loaned. And we had a WBT tube on a pole mount with 70 kilohertz and a 120 kilohertz transducer, downward looking. And so this was our ground truthing vessel. These are data from that vessel using the broadband acoustics, downward looking. This is the 70 and the 120 kilohertz channel. So on the left-hand side, you have depth and you have time. This is about an 8-minute record. And we were weaving back and forth across the front. So you can see that this is one crossing. So we're from outside the front to inside the plume. And then we turn around and we travel from the inside of the plume out. And you can see that the plume, the scattering from the plume, reaches all the way down to the bottom. And so it's highly non-hydrostatic, and so trying to understand those dynamics is part of what this experiment was about. So these are the data, the same data, and superimposed in magenta, you see this is the salinity contours. So this is 26 parts per thousand, 24, 22, 20, and so on. And you can see that the salinity contours match the acoustic scattering fairly well. However, there's very strong acoustic scattering at the front of the plume, and that gets weaker and weaker as you go back. And so one of the things we wanted to do was we wanted to really get underneath that plume front with the Remus 100, with the transducers looking up, in order to get to characterize the broadband spectra of that front. So these are data from the Remus 100. On the left, you basically have, this is no longer depth. If you remember, the transducers are looking up. So this is range from the AUV. So the surface is at the bottom of the image. So it's a little bit confusing. I've put an arrow here indicating that this is up. So the top panel is 160 to 260 kilohertz, and the bottom panel is the 260 to 410 kilohertz. And this particular set of data is a region just before we hit the plume. So we're traversing, we're out in Long Island Sound water, and what you see is that there are sediment plumes coming up from the bottom. And so you can see that because it's sediment, you have more, it's a stronger scatter at higher frequency, so you see it more in the higher frequency panel. And you can see the surface, and you can see that there are both waves on the surface, but also that the AUV is not traveling completely steadily at one depth. So those two little boxes that I've outlined are going to be places where I'm going to do scattering spectra to see if we can characterize, not just look at an echogram, but actually characterize what the spectrum looks like. So you keep going, and now you hit the front. So we are now underneath the front, looking up. And you can see that you can still see the sediment. So before you hit the front, you can see the sediment. You hit the front, and you see a huge scattering response. And so the question is, what is it that's giving rise to this scattering? And so I've chosen a whole bunch of different boxes, and I will show you spectra from those different boxes. You keep going, and so now we're passing the front, and you can see that the scattering is decreasing with time. You can see this tongue, which has developed here. And the other thing that you can see is that there's a layer close to the surface, which is also developing. I'm going to call this region the transition region. Acoustically, it's quite complicated because you're getting scattering from multiple different mechanisms. Okay, so if you keep going, and now you are basically, you have the fresh water up above you, and you can see that there's this strong scattering layer close to the surface, and we're sort of interested in what is that. It's about 1 meter thick scattering layer. Okay, so here are the scattering spectra for the different regions inside. So the magenta shows you the scattering for the region inside the front, the really strong scattering layer inside the front. The sediment that we saw in front of the front is the magenta, and that's got the traditional frequency to the 4th power response. So so that's pretty easy to interpret. We think that the scattering in the front is due to bubbles. And so the models that I'm showing you here are basically the David Farmer scattering model with the measured distributions that he measured for bubbles. And I will show you what that model looks like in a minute. When you go to this region here, which is this layer that you see just below the surface, behind the front, you can see that it's got a frequency to the +1 spectrum, which is consistent with salinity microstructure, and we think is probably just the thinning of the plume that you have behind the front. So it's very high shear, very high salinity gradients, and that's where you're getting the scattering from. I went to, just to persuade myself that I was doing this correctly, I went to multiple different locations to look at the scattering from sediments, to look at the scattering from bubbles, and this picture is pretty consistent across all of our crossings of that front. So the problem with bubble size distributions is that we didn't really have any mechanism out there to measure bubble sizes or bubble size distributions. So I basically had to go to the literature and look and see what has been measured for bubble size distributions in by using different techniques and in different locations. And so here are just some of the results. This is 1991 Vagel and Farmer scattering measurements. And these are the bubble size distributions that you get at different depths from the surface. On the right, this is a 2003 paper by Thorpe et al. These are bubble clouds distributions in Langmuir circulation. And then on the bottom right, you have a paper by Grant Dean et al. This is 1999, and this is bubble size distributions in the surf zone. And they're plotted on different scales, but the Langmuir circulation and the Vagel and Farmer distributions are actually surprisingly similar. And so I decided to just pick one of those distributions and use that as my bubble size distribution in the plume, which I really don't know if that's accurate or not, but that's what I chose to use. And so then I had to choose a scattering model, and there are various different ways of approaching this. But in the end, I used the blue curve is basically target strength as a function of frequency for an individual bubble. And the two different blue curves are just two different size bubbles, just so that you get an idea of what happens when you change the bubble by an order of magnitude in size, what happens to the scattering. And I just used this mechanical oscillator model that David Farmer had used in his paper. And this model is not quite accurate at the very highest frequencies, but if you look to the right and you look at predicted volume scattering based on the bubble size distribution and these two different models, you can see that you get very different results if you don't correctly account for the damping of the resonance, which you get for the mechanical oscillator model. So going with the mechanical oscillator resonator model for bubbles and the bubble size distribution measured by Farmer at about 2 meters depth, that's where we get the model that we see here, which I've plotted and agrees fairly well with our observations, our measured spectra. And so we're pretty certain it's bubbles. If we go back, it would be really nice to have a resonator out there so that we can actually measure some bubble size distributions and confirm that that's what it is. Using the AUV, we also saw some pretty spectacular shear instabilities. And again, we can begin to characterize the mixing that occurs in these shear instabilities using the acoustic scattering spectra. And if you do that, you can see that this curve in black is the inertial convective microstructure model and the data, and you can see that they agree very well, so you can begin to extract mixing parameters as a result of that. That's something that we still have to do. And so we sort of feel like this is a very successful first use of a broadband echo sounder on a Remus AUV. There are lots of things that are still needed to be done, but we feel like this is a really good first step. We also had, I just have to show you this just because it was such spectacular data. So we also had the M3 multi-beam. And so when we went into the inner estuary, and so this is just an echogram, this is the 120 kilohertz depth as a function of time. And you could see these shear instabilities that developed. And we also had the multi-beam on board. And you can see here these same shear instabilities that we were seeing in the traditional broadband echo sounder. And they're now beginning to call broadband echo sounders traditional. And you can see these beautiful shear instabilities in 3D. So that's something we're pretty excited about. At the time, we were just playing really with the multi-beam, but we're hoping to go back and actually map these shear instabilities in 3 dimensions. There are obviously some problems with using AUVs in estuarine environments, especially on July 4th weekend. One of them is you tend to bump into a lot of boat traffic and other types of traffic. And this AUV was victim to a barge carrying July 4th fireworks. And so definitely some difficulties with that. Okay, so I now want to talk, the last thing I'm going to talk about is trying to characterize swim-bladdered fish using a different approach. Everything I've talked about right now basically puts us into the scattering regime where all of the frequencies that we've been using are well above the resonance frequencies of the fish that we have been imaging. And so the idea is, if we start moving down in frequency, can we actually measure the scattering response of the swim bladder? So the low frequency resonance, lower frequency resonance. So this is a system that Tim Stanton developed. You can find that I've put the reference in here if you're interested in reading the paper. This is an edge tech system that he developed. And the idea was to map the low frequency resonance. So here on the bottom left-hand corner, this is Atlantic herring. And you can see depth as a function of, this is a long track distance. And you can see that in the bottom left-hand side, you have what we're going to call unresolved, or just patches or aggregations of Atlantic herring. On the right, you can see that there are individually resolved Atlantic herring, and the reason you can do that is because you're using broadband acoustics, so you have that spatial resolution. And so Tim Stanton, and again, the reference is over on the left over here, used this system to look at scattering spectra for herring. This is 25 centimeter herring. This was done in collaboration with NOAA Fishery Sciences Center, Northeast Fishery Science Center, and Mike Jack measured the size of the different herring. So this is volume scattering strength as a function of frequency. This is a log scale, and look at the frequencies. We're talking 1 kilohertz to 6 kilohertz. And this is the resonance frequency of 25 centimeter long herring at depth. Now, one of the things that you have to remember is that as fish perform daily vertical migration, their resonance frequency of their swim bladders can change. And so on the right, you see an aggregation of fish, and you see that there's a mix of fish. So this is higher frequency peak, which is a mix of fishes 2 to 5 centimeters in size. And then this lower herring 25 centimeter peak. And so this is a really powerful technique. It's doing something that we haven't traditionally done in acoustics. And so Tim and I decided that we would try to develop a similar system, which would enable us to look at mesopelagic fishes. So this is a new platform. It looks like it's just in its concept stage, but in fact, most of the pieces are built. It's being put together. So we're within a stone's throw of having this system completed. It's a deep-toed system, and the centerpiece is this large 1 meter, it's actually a circular array on the bottom of the instrument, which is a low-frequency split beam array, so that we can measure the resonance frequencies of fishes in situ. However, in order to characterize a region as complex as the mesopelagic zone, we're going to have an integrated platform with not just acoustics, not just low frequency acoustics, but all other kinds of sensors as well. So this system has this low frequency acoustics. It has a suite of high frequency acoustics. It has a number of Simrad WBTs on it, BT tubes. It has the 500 kilohertz multi-beam. It has environmental sensing package with a CTD, dissolved oxygen, fluorometer, pitch, roll, heading, all of that information. But it also has this front end, which is a camera system. It's a pretty sophisticated camera system. There's an LED lighting array, which lights up about a 1 meter squared area. And we have 2 high resolution stereo cameras, which will allow us to actually image fishes and jellies and other organisms. And then we have a holographic camera, which will allow us to create 3D images of the smaller zooplankton that are less likely to avoid. And this is all connected via fiber optics so that we can do real-time processing. So we're pretty excited about this. We have our first cruise in August 2017 on the NOAA Henry Bigelow. And I look forward to reporting on how that goes. And so I just want to sort of wrap this all up and sort of say, well, where are we with these platforms? Well, it turns out that broadband acoustics on a hull-mounted ship is a pretty good sensor for the continental shelf. You can pretty much get to the bottom with all of the acoustic frequencies. And so you don't really have to have a in situ platform. There are circumstances where it would help. For example, if you want to do a rapid response sort of situation where having a vehicle would be great. But you can do it with the Neil Armstrong. The Neil Armstrong is no good if you go out to, if you're interested in mapping really shallow environments. We tried that. It just becomes a big hotel, a pretty expensive hotel actually. And so, you know, we've been using these Remus vehicles, and we're going to continue to do that because we've collected some really good data with those. So we have this deep sea towed instrument, which we're hoping to deploy to look at mesopelagic regions, which are the deeper regions. And so where from there? So this is just sort of where I envision, you know, my own research taking me. One of the things that I'm interested in is developing an extended duration, larger Remus that can actually house more acoustics for a longer duration in addition to other sensors. This is an extended duration vehicle that you could put out in response to in a rapid response mode to look at extreme events. And I think, for example, if you're interested in the interaction of, say, squid and warm core rings, this is the kind of instrument you're going to need. It would be rated to 1,500 meters, so you could also put it down to look at the mesopelagic ecosystem and look at organisms down there. I'm also interested, I submitted a proposal which wasn't funded, but I'm not giving up, to get a jet yak with broadband acoustics, because I think that's going to be really useful for some of these really shallow environments. And so, the one thing I haven't talked about at all is what I'm going to call the elephant in the room, which is autonomy. We have all of these autonomous vehicles with large data sets. And right now, we just go out and we blindly collect data, and we don't really use that data in real time to inform the vehicle of what it needs to be doing. And part of the problem is, how do we analyze the acoustic data? What are the metrics? What are the parameters that we're going to extract from the acoustic data to inform the vehicle? And then we actually have to have somebody working at the vehicle end of things to incorporate that into the autonomy. So that all-around system, in order to make it truly useful in these rapid response sort of environments, and to track features, because you can't just go, even a extended duration vehicle is only going to go out for a day or two. You can't do everything. You can't survey everything. And so you want to get smart and perhaps only survey hotspots, or only collect data where you have hotspots. And so I think thinking a little bit into the future, how to use these vehicles in an autonomous fashion is going to be beneficial for all of us. And so I think that's all I have to say on new platforms, but I would be very happy to take any questions either from the room or from the online audience.
Thank you, Andone. We're a little bit over time, but if anybody in this room or would like to, we can just do maybe 5 minutes of questions for anybody who has the extra time to spare. Anybody have questions? I've got my group chat open too, so people can write in with questions. And Andone, I'm going to ask you if you can send me your first 2 slides, because I didn't hit the record button until you were on slide 3. So I'm going to post those in addition to your video so that everybody can see everything.
When do you want me to do that?
Anytime. You just, the first 2 slides would be great. There we go. Perfect. Now it's captured on video.
Okay. Do you need any more, or are you done?
No, that's good. I don't see any questions here. I think there were a few people who are already dropping off. I know students here had class. So again, I want to thank you. And within maybe a few hours, we'll have this up live on the website so people can go and watch it over and over again. Good luck giving your Charles lecture too.
Hi, Jan.
Oh, here we go. What? Yes?
This is Jim Simmons at Brown.
Hi.
Just one point about the last slide and the autonomous problem. It seems to me that dolphins and porpoises have solved that, and it might be worth looking in that direction.
It may very well be. my initial quip is to say I'll ask them, but I agree. I mean, obviously they're doing this very effectively, more effectively than we are. For the most part, when it comes to autonomy in the context of active acoustics, I don't think very much has been done in that region. I think it's something which I think would be very beneficial for us to spend more time thinking about as a community. It's going to take people who have an expertise in that region, in that area. That's not me, but I'm certainly very excited to work with people who do.
Anyway, it's an interesting thought, anyhow.
Yeah.
All right, well, we're signing off. Thank you.
Thank you.
Thank you. Any other last minute questions here? All right, well, thank you so much, Andone, and we hope to see everybody back on January 9th for Passive Acoustics.
Perfect, thank you.
All right, thanks, guys. Have a great day.
I have a question.
Yes.
Your data.
Okay, hold on, I gotta.